Hello, my wonderful Physics 2212 classmates. This is Lab 5 that I'm going to be sharing with you today. So let's get right into it. As an introduction, the purpose of this lab was to record and model the behavior of a bar magnet falling down a conducting metal tube. The lab centers around Faraday's law, magnetic fields, magnetic force, and Newton's second law. Here we have the equation for a magnetic field due to a bar magnet, and then this changing magnetic field as the bar magnet falls creates a change in flux, as shown in Faraday's law, which will create an EMF, which will create a current, and this current creates a magnetic force, and this magnetic force creates an acceleration to the bar magnet, which counters the acceleration from gravity. So we will get into all of that. And here's a representation of Newton's second law. I don't know who the guy on the left is. So, the actual experiment is as simple as dropping the bar magnet through a cardboard tube and a tube wrapped in aluminum foil. It took roughly 0.15 seconds to fall through the cardboard tube and about 0.5 seconds to fall through the same tube wrapped in foil. Now, as a preview of our results, in our computational model, the magnet took 1.394 seconds to fall through the tube. As the magnet falls through the conducting tube, the changing flux in each section of the tube should create currents which impart a magnetic force on the bar magnet. This force is counter to the magnet's motion and the acceleration due to gravity, which slows its descent. The tube in the computational model is a series of conducting rings, which simplifies the calculations of current. So, for the experiment, the system is just the bar magnet and the tube, and the surroundings is the entire Earth. The bar magnet starts with 0 velocity, and the width of the foil is estimated to be 2 millimeters. Let's start with our code. So we set up the physical constants, as always, and then our dimensions of our tube. Next, we input the mass of our bar magnet and the magnetic moment of our bar magnet that we calculated from a previous lab. Now we actually create the bar, as seen in the code below. And now we create a function for calculating the magnetic field from a magnetic dipole, as you see right here. And this uses the equation we went over in the introduction. Now, the Faraday's law equation for magnetic flux, this is right here, which will be used later in the lab to calculate the magnetic flux from the magnet falling on each of the metal rings that make up the tube. Now we have the force of gravity, which is as simple as the mass times the gravitational constant. And then we have the magnitude F on the magnet, which we start out as 0, and we will add up the magnetic force from each ring to get the total magnetic force. So first we need the flux, so we use that equation that we just set up earlier, and then we use it to find a current in each ring. Now, using this, we can manipulate it so that we can use the current and the magnetic field to find the magnetic force on the bar magnet from each ring. Then we add all of these together and combine it with gravity to get the net force. Now we just need to use this to update the bar's velocity and the bar's position. Then we just plot it, and here are our results. So you see, it reaches a constant velocity and stays at through the majority of its time falling down. So the difference between the experiment and the model and the sources of error. So the magnetic moment we calculated from a previous lab may not have been very accurate to the magnet we were using. We also did not wrap the foil around our tube very tightly, and it wasn't a very thick layer either. The assumption of using rings to model the current flow might not reflect the current flow in the real experiment, as it's not rings, it's just a cylinder of foil. So this all combined could have caused our model to be longer than the time that was falling in the actual experiment. So what if? What if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? The current would increase, and thus magnetic force on the magnet would increase. This would cause it to fall much slower. And what if holes or slots were cut into the tube? the current would not be able to flow in vertically stacked rings like we did in the model, and this would impede the current flow and thus decrease it overall and decrease the magnetic force. Thank you all for watching.